So I'm Jacques Coves. I'm working in CS Group, and I will present you big data analytics for natural disaster management, especially in the context on flash flood forecast using AI. Few words. Just look at the picture that I've put on the first slide. It's one of the use case that we are going to talk later. It's in south of France, in the city of Nîmes, which is known for Roman arena, but also for its main type of large type of disaster and flash flood. I will give you some more detail about that. In this presentation, I will focus first on the context of the floods, different type, and mainly flash floods, not to make a lecture on flood and hydrology, but to give you the reasoning on why we are working on this subject and the specificity of this type of flood and the consequence that they have for the modeling, and especially why we are trying to use AI modeling for that. So we present some key features of these floods, why we choose to work on that, why we choose to work on the use case of the city of Nîmes, and the methodology and different scenario that we are trying to apply. Of course, if you have any question, just write them in the chat. I will be a pleasure to answer. I don't know how long will be the presentation. I think we'll have time at the end to answer. So I hope there is no many hydrologists in the attendees, because I made some very large and gross simplification for a large public. We can divide the flood in two main types. Actually, it's not completely true, but for our case, it's interesting to divide that because of the characteristic of this flood. I made two columns, as you can see, what I call plain flood. This means flood occurring in large plain like Danube, Rhine, the Seine, and very large river that you can have on Mississippi over. And everybody heard about that, usually on the TV, and see a dramatic image of that. At the opposite, the flash flood were completely different. So the main characteristic and difference is the cinematic of the episode. Usually, a plain flood is occurring slowly. It's lasting. I mean, you have many days to be ready in advance, because you need to have precipitation for several days. And usually this type of event will last for at least several days, sometime weeks. At the opposite, the flash flood will occur in a few minutes, very suddenly. Sometime you have no sign in advance, because the precipitation are very local. And usually the episode globally don't last too long. It's hours or days, let's say, maximum. This occurrence is very progressive for a plane. This is a kind of advantage, because you will be able to prepare yourself, prepare all the security people who have to, and the municipality, get ready for the flooding. But it's not the case for a flash flood. Even if we have, I would say in Europe, we have good meteorological agency, and we are not surprised when they come. Sometimes it happens that they occur not exactly at the time that the previsions were done, or not exactly at the place that was forecast. So it's always a kind of bad surprise. The morphological environment, I mean the environment where you can find this type of fluid. Plain is, as the name is say, it's usually large area, more or less flat, at least smooth topography. For the flash fluid, I would say we have two different sides. Sometimes in mountains with a narrow valley, and then you have a phenomena of concentration of the water, acquiring a strong strength and speed and pushing down a lot of materials, rocks and so. But on the other side, and that's the one we are going to study, is in the urban area, which produce the same effect on the water flow. This means we have all the buildings, streets, infrastructure, and so on that will collect all this water. Mainly the water will flow, I would say, at the beginning in a river, then channel, pipe, and then over the streets. And and there is this phenomena which is more and more important in our city because there is more and more pavement, impermeable surface with a lot of construction, very place to absorb the water. So this phenomena is getting bigger and bigger. Extension of the phenomena, of course, in plains, by definition, is really large. It could be part of a region or part of a country. Flash flood are usually a few square kilometers because it's very concentrated in depression or valleys or in the street of a city. To work on this type of event, we need data, of course, and we have been speaking before about data. And of course, when you are working on plane modelization, you would like to have very good data with good precision, but you can manage to have a lower precision data, which is absolutely not the case for flash flood, especially in urban area, because you have to take care of, I would say, every object, every infrastructure existing, which is going to guide the water flow and to have an important impact on the height of water and the speed. So the main feature, which is important, and you will see later, they are important for the modelization and they have consequences. Urban flash flood, I will not talk about flash flood in the mountains because it's very similar, but not exactly the same regarding the modelization. Urban flash flood, you have to take brutal occurrence. Okay, this means you have very few time to get ready. They occur very often in cities or at least populated area. This means a risk, dramatic risk for the human being, but also for all human activity. This means industry, services, infrastructure. So very often the impact is very dramatic, even if the area, the surface area is not so large. And so that's, and as you know, the economic point of view is very important. Therefore, there is a strong need for modeling this event because it will addressing many people, sometimes with human life loss, at least large economic cost. And so there is a strong requirement to be able to model this event and to elaborate some forecast that you can rely on. This is very important. Why? Because if you have a good modelization and forecast of the event, you will be able to anticipate the event. This means on the long term to be ready to plan, so to have infrastructure planning, modifying some infrastructure, adding, enlarging pipe for to evacuate the water, take into account the feedback of the recent event, what happened, what was good and bad, what we should change. When the crisis occurs, if you have a reliable forecast, you will be able to trigger reaction on the right time. This means early enough, but on the right time. This means if you have an alert to the an alert system to the population, you may want to close some area that at low level. You want to close the underground parking lot and stuff like that. Of these actions, you know them, but you have to take them in advance, not too much, and you have to be sure that your flash flood event is going to occur. The worst would be to take action for nothing, because the next time the people they will not listen into your recommendation. They will stay park their car in the parking lot, and then they want to save the car, go in when it's completely flooded, and it's the bad event then. And of course, I would say more generally to decrease and to avoid the consequence. I mean, you cannot avoid the rain to fall down, but you can try to decrease the effect on your life and the economy. So that's why there is a strong need for this kind of modeling, like everywhere, I would say. But here there is many action, and you will see that it's not so easy because of the characteristic of the ruling. This characteristic, they stress, they put some very difficult constraints specific on the modeling of this event. Traditional modeling, I would say hydrological, hydrodynamic, tend to be based on a modelization of all the physical parameters that are influencing the event. We'll see a list later, but I would say the topography, you need to have a digital elevation model. You have a ground occupation cartography maps. You have to precise data on the precipitation, when and where. All this information, you need them precisely for each event. And you want to modelize in a hydrological model, you want to modelize very carefully all these parameters and how they influence the event, which is very difficult for numerous reasons. All these data are, I would say, numerous. It depends on the place, but they are very heterogeneous, very different. In frequency, in format, and so. And sometimes, in some place, very difficult to acquire, meaning you don't have the sensor, you don't have the historical data, you are missing at least a part of the physical parameter. And so it's difficult to set up and to tune your model. So that's why in very few places, actually, if we take Europe, I mean, there is many places we have good modeling, but if you go outside Europe or US, it starts to be very difficult even to have some data. And if you don't have the data, the input data for the model, whatever is the model, it's really impossible to predict anything. In addition, the tuning of this type of model is difficult, it's long, it takes time, it's sometimes very difficult to converge. And usually they use a lot of CPU time, which we'll see. It's a kind of problem for the operational agency, because when you have a flash flood, things like the precipitation, are changing very rapidly. And if you have a forecast 24 hours before, there's a good chance that it is not precise enough, or it turned to be wrong 24 hours later. So usually people in charge of this agency, they try to have something model that they can re-execute rapidly to take into account the most recent data. I'll give you an example. When you have a rain radar, I mean, it's radar on the ground, checking for the rain, precipitation, water drop. Usually you get information, a map, every 15 minutes. And that is a very significant, very important data you have to input in your model. If you're able to rerun your model every 15 minutes, you are sure that you have the last and the best input data to run your model. And it's the same for the wind direction and the actual situation in the city, for example. So it's very important to have this rapid running model that you can re-execute at least, I would say, every hours, for example. And hydrological model, usually you need more like hours to run all the parameters and to make all the calculation, because there is a lot of calculation for each point of we'll see how it's calculated. You calculate several parameters for each small place in the city. So this characteristic push us to try to figure out how the AI could help us, since in an AI approach, it's completely different. You don't, of course, you need the data, but you don't try to figure out exactly all the physical parameter will interfere, interact, and change the result of your model. So in our model, in our project, which is, I didn't say it before, it's Extreme XP, it's a European project, and we are in charge of one use case in the project, the modeling, the flash flood modeling. And so the main idea was, how can we use this AI model to simplify the way we get good prediction, and how we can act on that, and what way can we simplify the process in order to make it available for several places where they have nothing because they lack of data, or they have bad quality data, missing data. And second point, once the AI model is trained, the goal was to have something which is running fast enough that we can use it and reuse it during the crisis. That was the global goal objective we are working on. And I will show you what the way we are trying to address that. So as I said, the two main axes was reducing the constraint. So it could be less data or lower quality data, not so dense, lower frequency, missing series and stuff like that. And also an execution which is simple. I mean, because usually our users are not computer specialists. They have a good background in hydrology, but not in a computer. So it should be easy to activate and to run, and also a short execution time. Of course, we all know that if we are talking about AI modeling, we need a lot of data for the training phase, good data, representative data of what we want to figure out, which is a very tough condition to fit sometime. And also, we need a way to verify our results compared to something that we are taking for the truth, which is kind of the equivalent of the labeling for different type of data. So by chance, we had some connection with the city of Nîmes. Also, you can see if you show my cursor. Nîmes is in the southwest of France. You can see on the map on the right in the corner. And in this, the color map, you can see, so it's close to the Mediterranean Sea. You have the Rhone River here, and the city is here. So it's about, let's say, 30 kilometers from the sea. And what's very important, just in the back, you have we call the Cévennes mountain, which is the age of the Massif Central in France. Not very high, but high enough. And what happened during the autumn, mainly autumn, we have a phenomenon, a meteorological phenomenon. We have the water, which is still hot compared to the inland, a lot of evaporation, and then depending of the pressure, a lot of water, vapor water, coming from the sea to inland and hitting the mountains, and then they start to go down, and it can last for hours or sometimes for days when the clouds get stuck on the mountains. And you can have like I don't know if it's something that you can figure out, but it's 300 millimeters of water in 1 hour, sometimes even 400, which is a lot. And when it's in the countryside, one part is absorbed by the ground, by the soil, but not in the city. You have satellite image from the city here. You can see that it's a whole city was built by the Roman. We even have an arena here in the center. All the city center, it's all the houses with narrow streets, and there is several small rivers coming down from the mountains and to passing directly through Nîmes or just before side Nîmes, but the concentration. So it's really I would say the worst condition for this type of event. So the city is rather large, the middle class, 100,000 residents. Of course, like all this city, the stress of urbanization, ground impoverishness increasing, and a lot of runoff on the surface runoff increasing with all the buildings. And also something that happened at least in France, in the south of France. They used to have a natural drainage channel, let's say some kind of small river, was flowing down from the northwest to the southwest. But with all the building urbanization, they tend to obstruct them. Sometimes they cover them. And so it reduced the capacity of for the water to go through and to be directly directed to the sea 30 kilometers later. So that's for the condition. And as you have seen on the first line, the first line on the front was a dramatic event in 1988. People die. I think it was 600 million euro of damage. 30 kilometers of water pipe was just destroyed, completely destroyed. And it was a very dramatic event, not even for the city, but for the region. And they start to have a new infrastructure starting at that date. And now it's a proof that it's effective because we still have precipitation, but usually no such damage and no human loss, human life loss. In Nîmes, they do have an existing modeling system, which is called ESPADA, which is an hydrodynamic modelization. But as I told you, for example, they are able they can run it, I would say, not in real time, because it takes time. So what they run it in advance, and they have different scenario, and they check from the output of the model, they check on which scenario, flooding scenario they will have. This means, okay, we are at level 2, 3, and so, and we know by experience that this district of the city will be flooded with, say, 50 centimeter or less, and so on and so on. And you see, they cannot rerun the model because of time, CPU time consuming. And during the crisis, these guys, they have something else to do and to figure out that to rerun and to wait for a model. So that's a point. So they have a model running and they have some data because they archive all the data, they install many sensors since that time in 1988, 80. And we had a good relation with the city council, and they were okay to let us use this historical data. One difficulty is that because they make a lot of work, infrastructure on the sewage, on the water evacuation, and so we have different type of situation, and we have to be careful of what the date of the data that we use and what was exactly the urbanism state at that time, because they dig new reservoirs, search tank, and so to evacuate the water. And also, we have also a lot of documentation for the main event. That was the good point, and we knew that with this set of data, we were able to verify all our results against some, I would say, concrete observation and other model. So that was acceptable for us to train first the AI model and also to validate the result regarding existing data and existing result. Here is I would say, the global general methodology that we are applying in a project to set up the AI model. So I would say two main phases. The first one was to build a new hydrodynamic model. Why to build a new one? Because there is already one existing for the city agents. Because we wanted to have something that we can completely, fully control, parameter and splat and run as we want, and that we are able to verify against the historical data. So that was our first phase. And the second phase will be to build, to set up the AI model based on some of the data, of course, and to verify the result against the hydrological model with different circumstance, different event. So on the figure you see on the left here, we have all the data, what we call ground description data. It's mainly the dam, the digital elevation model. We see what type of data that we use with the slope, rugosity, all the buildings, streets, and so. And then historical data about the different events, mainly precipitation. From different source of data. We have sensor and we have the rain radar. Here. Okay, we have some pre-processing, we'll see later, mixed all together, and then we are able to run and tune the hydrological model. We rerun until we get some acceptable validate hydro model compared to the historical data. And the advantage we have here is that having this hydrological model, we can rerun it, changing the input data to produce event simulation to increase the number of events that we have here. That's a historical event. Actually, there is not so many to train an AI model. So with this hydrological model, we are able to build, simulate event, meaning event is a situation with precipitation inducing flooding in the city. And then, so we have, that is a database of historical and simulated event. And this will be used for the training of the machine language training, testing, and validation of finally of the AI model. That's one of the advantages. Usually, if you check the historical model, let's say you have one event, not even significant event every year. So it's very few. Okay, an event is a lot of data. So you can consider it's a lot of data. But to be representative for the training, we need to have more than that. So that's why we implement this methodology to be sure that we have enough set of events to train the machine learning model. A word about data complexity, because that was also one of the topic of the project, SpaceM. It was to process situation data with some complexity. In our case, we need to address data that are related to space, X, Y. It's most of the time it's a time series with various frequency sampling when we have sensor, and of course different format. We have a raster, vector, grid format, time series, all kind of format. I mean, computing format. Spatial resolution, for example, if you have a sensor, that's a rain gauge, okay, you're measuring the amount of water in one point. When you have radar, rain radar, it's a grid. So they give you an amount of rain, of precipitation for one elementary surface, a grid. And then you have to mix this information. And then you have to register them to make them geographically. You can really stack all the different information. You are sure that they are on the same place. Then the temporal registration, because sometimes you have a series, but they are not exactly on the same timing that another type of data. Okay, you have to shift this data to be able to compare the data on one place at one time and be sure that you are not mixing different things. Of course, you have some cleaning because they are not adapted for the modern artifact, like always when you have data management, you know that. So we make an intensive use of GIS, I mean, to work on this data because the base is a geographic data plus the time series and also libraries or I mean, image processing sometime and mainly for the extrapolation, fusion of data, and so on. Another point about the complexity feature is there are what we call massive data, because for some of the data we have very long time series or very massive grid data like the rain radar. For example, if you want to calculate a rain radar, it's one value for each 500 meter square, and they are covering about a circle about 500 kilometers. So that makes a lot of data. And also we were lucky because in France they have a program, they are flying aero biplane, a LiDAR, high resolution LiDAR. So the city of Nîmes, we got this information. This means you have one point measuring X, Y, and the elevation of the ground, mainly. Usually you get several points for each meter. That's something that we fuse the data with other type of topography data from the French Geographic National Institute. And just a word to figure out in the calculation, we divide the surface, say the surface of the city, in small triangle. They have less than 50-meter sides. Why? Because to represent the water flow, we have to divide the surface of mainly the streets, in small triangle to calculate an information at that level of precision in order to produce something coherent with the reality. If you have a larger grid, I mean, you're going to mix the very different objects on the ground. For example, you can mix a part of a house with a part of the street. And it's at the end, it's completely wrong because in the urban flow, each structure above the ground is important. So it's one of the heavy work to do is to prepare this surface and this triangle for the calculation. And there is, okay, and then at the end, the output, the result of the model is a value of the height of the water. For each triangle, the height of the water. Sometimes we'll get also the speed of the water for each step of time. So if you're calculating that for, let's say, 24 hours, and you calculate it for every, let's say, 15 minutes, for example, you see that it makes millions and millions of points to calculate. That's why the hydrological model is so long to run. That's the way hydrodynamic model is set up. You have, just to figure out how rapidly, high resolution digital elevation model, which is here a mix of the LIDAR data and the surface topographic surface, and you have to mix them. Then we have another data, which is, I would say, the ground occupation, and we have to extract the building ground footage, because where we have building, we have no water flowing. Same for the street, because we consider that the street are the main channel for the flow when they get out of the river channel. Different structure is let's say, something which is a mix of buildings. Sometimes you have to mix the different building to make a kind of small island, which is not only one building. You have to define the catchment, the limit of the river basin, catchment boundary, and also to define if you have attributes, I mean, inflow, I mean, smallest river who are coming in the area. Up to now, all this cleaning of data is partly manual, partly automatic. We have been able to automatize a good part of this work, but not everything, because there is still some area that you have to have a human work on that, but it's not to be acceptable. The idea would be to automatize that at the maximum, so it would be easier for a non-specialist to do it. Okay, then I won't go into much detail. You have to find what we call the holes, mainly what there is no water, to make a 2D mesh. And then you enter the precipitation layer data, which is a surface of water with the amount and for each timestamp. You mix that, you have the time series here, and so you are able to figure out to tune your hydrodynamic model. Okay, that's done in the project. Now I will give you two examples of scenario how we can use the AI model once it will be, which is not completely done right now, when will we be verified against the hydrological model. For example, in many places, you don't have high quality data or high resolution. And for example, here, what we are trying to do is to figure out if we have a bad quality digital model, let's say with a bad low resolution, like 100 meters, are we able to, by deep learning, increase the quality to have a high resolution model, let's say about 30 meters, something, 20 meters, 10, depends. And then with different classifiers to extract the building, the street, and structure, to enter that in the AI model, check for different events, and validate the result against always the hydrologic model. The idea is to define and try to find how we can accept low quality information as input. Because here in the city of Nîmes, we are lucky because we have, I would say, almost all the data that we need and in a good quality. But it's very rare. I mean, there is actually very few, even in France, there is very few cities where you can get all this set of data. So the idea is, because the AI model doesn't work the same way than the hydro, is there a chance to be able to set it, to tune it, that is able to give good result with lower quality or space or less frequent data as input? So we are working on that. And you can ask, okay, what's the interest, what's the objective? But the interest is that there is many places, even in Europe, where you don't have the data available. And even if you go, for example, in Africa, there is a very large city, think about Nigeria, we have basically almost no data as input. But there is a terrible flood event with hundreds of people killed in this event. If we were able to set up a model which is will accept, I would say, low quality input, and it will be a good progress because we will be able to apply it in many places. But the key point is to evaluate to what extent we can accept this low quality missing data and so on. Because the goal is not to just produce outputs, it's to be sure that they are reliable and that we can use it in operational condition. So that's one type of scenario we are working on. The second type, is to really surrogate the model. This means to completely substitute the hydrologic model, having the data in input. If we are able to set up this AI model, and it will be the good advantage, the main advantage will be to run it faster because it should be able to run in, I would say, minutes for a surface like a city. And then we'll be able to make some prediction. Like, for example, in this slide, we always need, I would say, data from the ground, okay, less, but can start from the state calculated n-1, let's say 1 hour before. That's one in the input for the model. And the model will give us the prediction for state at n. Let's say it's hours or hour plus 1. And of course, the first time we have to evaluate that against either model, for example, on historical data. But if we are able to set up this type of model, we'll be able to have easily more prediction and either to work on these the different data that we have in input, okay, like that. For example, we say the municipality has some plan to change something in the city, like building new buildings, modifying streets. We can modify that easily and run the model here faster and several times to see what's the consequence of this new situation in the city. Okay, that's the second type of use that we could have. So finally, conclusion, and then if you have any question, pleasure. So the objective was really challenging, and we knew it by the data, the amount, and very complex, and some that you have to adjust manually up to now, which is a limitation, and we try to work on that. To automatize this workflow. Automatize, of course, it would be faster, but it also does mean that I would say non-specialists will be able to use it and to make some test challenge or get some what if condition. If I change that, I remove this street, I enlarge this street, and so on. Today, you need to be like a computer engineer to make it, at least a specialist in GIS. The other point is the sensitivity of the model evaluation. That's very important to know to what extent you are allowed, I would say, to use the result. And if it's successful at the end, it will be interesting to modelize the potential. But as I say, if you are new roads, new building, infrastructure, if you close some river or whatever, what are going to be the consequence? If you do that today with an hydrological model, it's really a pain. Of course, it's possible, and it's done. It's done, but it's you are limited by the amount of work and the CPU time. And of course, it will be a chance to apply that in a place where you would have not so many data available. Make this a prediction. Thanks for listening to me, and if you have any questions, it will be a pleasure.
Thank you very much, Mr. Jacques. I don't see any questions. Oh, there is one in the chat if you want to answer.
See you in the chat. Yeah. Thank you. Could you the potential source of can you read me the question? I don't see.
It's asking if you could repeat potentially the sources of your models, from what I'm understanding.
Yes, of our maps. Okay. Yeah. Okay. The data are coming mainly. Some part are coming from the National Geographic Agency in France, I would say, and the other are coming from the city of Nîmes. I mean, I would say that all the information on precipitation, historical events are coming from the city, from the archive there. And the other one are coming from public, it's all public data. Even the LiDAR data are public. You can download it on the National Geographic Agency. You can download it by department and so on. And then you have to process them, but there is no I'm thinking about it, except the data from the event, historical data from the city, everything is public. So this means that it could be done probably in many places, I suppose. Yeah. And then all the geographic processing are done with open source, which is QGIS. You have everything in QGIS you can then, or sometime with open source library. In our company, we don't use. I mean, we tend to not using cost. I mean, we use many open source solutions.
Okay, thank you very much.
Did I answer the question?
Yeah, more than that.
Okay.
Thank you very much. Okay. Yeah. I was just interested because we had some issues in Greece with some, in Larissa and the area of Thessaly, we had something similar, a phenomenon like some floods. I was just interested.
I think
how it could be approached.
All around Mediterranean, you have this phenomena because there is the hot water, and as soon as you have some mountains inland, I mean, it blocks the clouds and all the water fall down in the summer. Yeah, I was in Athens last year, and we have the same kind of flash during the meeting.
Mm-hmm.
Thank you. It was a good application.
Okay, I don't believe I see any other questions.